Okay, so we've got the generating functional of correlators, and we've calculated the correlator phi squared. What I'm going to try to do now is I'm going to try to show you that we really can learn things about quantum field theory in 3+1 dimensions by studying the quantum field theory in 0 dimensions on a point. And the first thing that I want to show you is if we look at this expression, we notice something. If you take a look at the coefficient, let me just put this down. The coefficient of minus 1/2 phi squared in the exponent, okay, of the integral. So look at z of j. An exponent, let's say, of integrand of z of j, this is equal to alpha. So what that means is the coefficient of minus 1/2 phi squared, again in the exponent of the integrand of z of j, to the minus 1, so that means 1 over alpha, this is equal to the 2-point function. Now, this is absolutely obvious and clear in this 0-dimensional example. Now let's come back to 3+1 dimensions. So let's go back to red. So look at 3+1 dimensions. Look at 3+1 dimensions. In this case, what is z of j equal to? Well, z of j is equal to, it's an integral d phi. We have e to the I. Then we've got an integral d4x. We've got 1/2 d mu phi minus 1/2 m squared phi squared. So that's the action term. And then we've got an integral d4x. This is the term where we introduced j of x. J of x is often called the source. It's the term where we introduced the source. And now I'm just going to rewrite this slightly. So what I'm going to do, remember my rule. I can take this derivative, move it from this field onto that field, but it'll cost me a minus sign, okay, to do that. So that's the rule that I'm using. Again, I hope by now you're very familiar with that rule. So we'll get, this is an integral, d phi. After I've done that, both of the terms will be negative. So let me pull out the minus I. We'll have an integral, d4x. We'll have 1/2 phi. Then we will have d mu plus m squared phi. And then we'll still have the integral d4x, j of x, phi of x. Okay, good. Now, what did we learn from the above? We learned that the coefficient of minus 1/2 phi squared in the exponent of the integrand of z of j was alpha. So let's look at the coefficient of minus 1/2 phi squared. So the coefficient of minus 1/2 phi squared will be what? So we'll have an I, because there's an I sitting there. The minus we can forget about. And then the thing that multiplies the two phi's is d mu plus m squared. So this is what this coefficient is. It's I d mu plus m squared. So what is the inverse of this coefficient? Well, the inverse of this coefficient will be I d mu plus m squared. Let's call the inverse g of x comma y. And this, if I multiply something by its inverse, I must get a 1. What is the 1 in 3+1 dimensions? Well, it's kind of natural to put here the delta function on x minus y. And explicitly, let's just be completely explicit. by the inverse of this coefficient, we mean g of x comma y. But by now, I'm sure that some bells are ringing, because you know that d mu plus m squared g of x comma y is equal to minus I delta 4 of x minus y. And from this equation over here, you should immediately be able to identify that this is exactly the Green's function that we studied before. And you might remember, or you should remember, that we showed that the Green's function was equal to the time-ordered correlator of phi of x, phi of y, naught, which we also called the 2-point function. So what's very nice is, in naught dimensions, where things were so simple, we could very easily recognize that the inverse of the coefficient of minus 1/2 phi squared, 1 over the inverse, the inverse of the coefficient of minus 1/2 phi squared is the 2-point function. And we could recognize that so easily in naught dimensions. In 3+1 dimensions, it would be harder to recognize it. But in fact, guided by your naught dimensional example, you're led to think, well, is this true or not? It's relatively straightforward to read off the coefficient of minus 1/2 phi squared. And then when we looked at its inverse, this is a very reasonable definition for its inverse. We learned that this is the Green's function, and that is indeed the 2-point function. So there's two things that I wanted you to get out of this. First of all, by thinking about the naught dimensional example, which is much, much simpler, we are often able to spot patterns that we wouldn't otherwise have seen. And then we can check, and these patterns often hold also for the 3+1 dimensional theory. So that's the first thing that I want you to get out of this. It's useful to study quantum field theory in naught dimensions. The second thing that I wanted you to get out of this is that it's a useful thing to know that the 2-point function is the inverse of the quadratic terms in the action. Good.